Ever wondered how a battery springs to life, or, why a gleaming metal gate slowly succumbs to rust? Perhaps you're observing the incredible energy released when you ignite fuel for cooking, or maybe pondering the perplexing phenomenon of the ozone hole that impacts our planet.
Right. All very different things, seemingly.
Exactly. All these seemingly disparate events, for the fundamental to the environmental, are intrinsically linked by one core chemical concept: redox reactions.
That's the thread connecting them all.
Welcome to the deep dive. Today, we're not just scratching the surface. We're embarking on a comprehensive deep dive into the fascinating world of redox reactions.
Getting right into the detail.
Absolutely. This isn't merely theoretical chemistry. It is, in essence, the invisible engine driving countless processes across nature, industry, and even within our own biological systems.
It really is everywhere.
For all of you aspiring engineers and doctors out there, especially those rigorously preparing for competitive examinations like JE Main and advanced NEET and your crucial board exams, mastering this chapter is absolutely fundamental.
Critical stuff for those exams.
It's not just about scoring marks. It's about building a robust conceptual foundation that will serve you throughout your academic and professional journey. And guiding us through this absolutely essential topic, providing the clarity and depth you truly need for competitive success, is our esteemed chemistry expert. Welcome.
Thank you. I'm ready to unfold the intricate mechanisms of redox reactions, ensuring that every single concept is crystal clear and practically applicable for your learning.
Right.
Our goal today is to equip you with the knowledge to not just understand, but to excel.
Our mission for this deep dive is ambitious: to completely demystify redox reactions. We'll take you on a journey from their classical definitions through the elegant electron transfer perspective into the precision of oxidation numbers, and finally, to the crucial techniques for balancing complex redox equations.
Covering all the bases.
We'll also highlight their immense practical significance, drawing directly from the expertly curated material you've provided, ensuring you are fully prepared to tackle any question that comes your way.
The ubiquity of redox reactions, a classical view.
So let's begin by grounding ourselves in the sheer ubiquity of redox reactions. It feels like they're everywhere once you start looking.
They really are.
Our source material really emphasizes their extensive presence across various sectors. Can you give us a vivid glimpse into just how pervasive these reactions are, perhaps with some striking everyday examples that highlight their importance?
Absolutely. Think about this. Chemistry itself, at its core, is fundamentally a study of how redox systems operate. It's not just one branch.
Right.
These reactions aren't confined to any single area. Their importance permeates diverse fields. You'll find them at the heart of pharmaceutical manufacturing, driving intricate biological processes within living organisms, powering heavy industries, enabling metallurgical extraction to obtain pure metals.
Like getting aluminium.
Exactly, like aluminium extraction, and even influencing modern agricultural practices. They are truly fundamental to life and technology as we know it.
Wow.
Consider the energy that fuels our modern world. The burning of fuels, whether it's the petrol propelling your car, the natural gas heating your home, or the LPG in your kitchen stove. These are all classic examples of redox reactions releasing energy. These processes are harnessed for domestic needs, transport, and vast commercial operations.
Okay.
On the industrial front, think about how we extract highly reactive metals like aluminium, as you mentioned, or crucial nonmetals such as chlorine.
Right.
These processes rely entirely on electrochemical reactions, which are fundamentally redox in nature. The manufacturing of essential chemical compounds, such as caustic soda, also operates on these principles.
Caustic soda, okay.
Even the everyday dry cell batteries in your remote or the lead-acid batteries that start your car. They're sophisticated devices that function on principles of redox chemistry.
Right, even batteries.
On the flip side, a common problem, like the corrosion of metals, for instance, the rusting of an iron bridge or a railing that's a slow but continuous redox reaction in progress.
Yeah, you see that everywhere.
Looking at broader environmental challenges, the emerging concept of a hydrogen economy, where liquid hydrogen is envisioned as a clean fuel source, and even the intricate chemical reactions linked to the formation and depletion of the ozone hole in our atmosphere are increasingly understood within the framework of redox phenomena.
Even the ozone hole. Wow.
Yes. So for students diligently preparing for competitive exams like JE and NET, recognizing these diverse redox phenomena in daily life not only makes the subject more relatable, but significantly strengthens your conceptual understanding for the challenging problems you'll encounter.
That's a powerful point about their pervasiveness. It makes you realize just how foundational this concept is. Let's unpack this with the basics. Historically, how were oxidation and reduction first defined before we even knew about electron transfer?
Right. To truly appreciate the elegance of modern redox concepts, it's vital to first understand their classical roots. Originally, the term oxidation was quite intuitive. It literally described the addition of oxygen to an element or a compound.
Makes sense. Oxygen is everywhere.
Exactly. Especially since dioxygen makes up about 20% of our atmosphere, making it a very common reactant. For example, when magnesium metal reacts with oxygen gas to form magnesium oxide,
MgO.
or when sulfur combines with oxygen to give sulfur dioxide SO2, these were seen as straightforward oxidations due to oxygen addition. Even the combustion of methane, CH4 plus O2 giving CO2 and water, involves oxygen adding and was categorized as oxidation.
Okay, so addition of oxygen, but that seems a bit limited.
It was. Chemists quickly realized this definition was too narrow. They observed that in some reactions, it wasn't just about oxygen addition, but also about hydrogen removal. So the definition broadened. Oxidation also includes the removal of hydrogen from a substance. A good example is hydrogen sulfide, H2S, reacting with oxygen. The H2S loses its hydrogen to become elemental sulfur, S. That's clearly an oxidation.
Right, losing hydrogen.
As chemical insights deepened, the definition of oxidation expanded even further. It came to include reactions involving the addition of other highly electronegative elements, not just oxygen.
Like halogens.
Precisely. Think about fluorine, chlorine, or sulfur. They all have a strong tendency to gain electrons. So when magnesium reacts with fluorine to form magnesium fluoride, MgF2, or with chlorine to form magnesium chloride, MgCl2, or even with sulfur to form magnesium sulfide, MgS. In all these instances, magnesium is combining with an electronegative element, and thus it's considered oxidized.
Okay, so adding oxygen or R electronegative elements, removing hydrogen, anything else?
Yes, one more expansion. Finally, the broadest classical definition of oxidation concluded with the removal of electropositive elements.
Removing positive ones, like metals.
Exactly. An example in your provided material is potassium ferrocyanide, K4FeCN6, losing potassium, an electropositive element, to become potassium ferrocyanide, K3FeCN6. That loss of potassium is seen as oxidation.
Okay.
So, to encapsulate the classical view, oxidation is the addition of oxygen or an electronegative element to a substance, or the removal of hydrogen or an electropositive element from a substance.
Got it. And reduction was just the opposite.
Pretty much the mirror image initially. Originally, reduction was simply understood as the removal of oxygen from a compound. A classic demonstration is the thermal decomposition of mercuric oxide, HGO, where oxygen is removed to yield liquid mercury.
Heating HCO gives HGNO2.
Okay. Similar to oxidation, the scope of reduction expanded. It came to include the removal of an electronegative element. For instance, consider ferric chloride, FeCl3, reacting with hydrogen gas to form ferrous chloride, FeCl2, and HCl. Here, chlorine, an electronegative element, is effectively removed from the iron's perspective, reducing it from +3 to +2.
Removing electronegative Cl.
Right. Conversely, reduction also encompasses the addition of hydrogen. Take the hydrogenation of ethene, CH2 double bond CH2, reacting with hydrogen gas to form ethane, CH3 single bond CH3. Here, hydrogen is added to ethene, signifying a reduction.
Adding H2 across a double bond. Classic reduction.
And finally, reduction was also defined as the addition of an electropositive element. Consider the reaction where mercuric chloride, HgCl2, reacts with stannous chloride, SnCl2, to yield mercurous chloride, Hg2Cl2, and stannic chloride, SnCl4.
Okay, that sounds complex.
It is, but focus on the mercury. HgCl2 gains more mercury, an electropositive element, to form Hg2Cl2, so that's reduction. But, importantly, notice that in this very reaction, the other reactant, stannous chloride, SnCl2, is simultaneously undergoing oxidation to stannic chloride, SnCl4, because it's gaining the electronegative element, chlorine.
So they happen together even in that example.
Exactly. And this brings us to the crucial overarching insight that became evident to early chemists. Oxidation and reduction never occur in isolation. They are inextricably linked, always happening simultaneously. Every time one substance is oxidized, meaning it undergoes a change defined by the classical rules, another substance must be reduced, fulfilling its classical definition.
It's a pair.
It's a fundamental, universal interplay that led to the brilliant coinage of the term redox, a powerful combination of reduction and oxidation to describe this entire class of coupled chemical transformations. It's a fundamental dance of chemical change.
Redox. Reduction and oxidation. So it's truly a chemical duet, never just a solo act. Let's try to apply these definitions. We have a problem from our source, problem 7.1, which asks us to identify the species undergoing oxidation and reduction in 3 reactions. Let's start with the first one, IH2SG plus Cl2G 2HClG plus SOTS.
Okay, let's break this down step by step for you. For the first reaction, H2S gas reacting with Cl2 gas to yield 2HCl gas and elemental sulfur solid.
Right.
Here we can clearly see that hydrogen sulfide, H2S, is losing its hydrogen atoms to form elemental sulfur. Recall our classical definition. The removal of hydrogen is considered oxidation.
H2S loses H, so it's oxidized.
Correct. So H2S is being oxidized to S. Conversely, chlorine, Cl2, is gaining hydrogen atoms to form hydrogen chloride, HCl.
Cl2 gains H.
And the addition of hydrogen is a classical definition of reduction. Therefore, Cl2 is being reduced to HCl. Take a moment to process that.
Oxidized, H2S, reduced, Cl2.
Got it. How about the second reaction? 3Fe3O4s plus 8Alis plus 9Fe plus 4Al2O3.
All right, for the second reaction, 3Fe3O4 solid plus 8 aluminium solid yields 9 of E solid plus 4Al2O3 solid. Let's analyze aluminium first.
Okay.
Aluminium, starting in its elemental form, Al, is gaining oxygen to form aluminium oxide, Al2O3.
Addition of oxygen
Is a direct classical definition of oxidation. Thus, aluminium Al is being oxidized to Al2O3.
makes sense.
Now, if we look at ferrous-ferric oxide, Fe3O4, it is losing oxygen to transform into elemental iron, Fe.
Removal of oxygen
Is a classical definition of reduction. So FeO4 is being reduced to Fe. This reaction, by the way, is a type of thermite reaction really important in metallurgy. Okay, oxidized, Al reduced, Fe3O4. That's clear. Now, the third one, which I suspect might be a bit of a trick, or at least hints at something more advanced. 3, 2As plus H2G, 2NHS.
You're absolutely right. This reaction, 2Na solid plus H2 gas yields 2NH solid, is indeed a pivotal one.
Why is that?
Because it elegantly highlights why we need to evolve beyond just the classical definitions of oxygen and hydrogen transfer. If you strictly applied only the rules about oxygen or hydrogen addition removal, it might seem a bit ambiguous, right?
Yeah, hydrogen is involved, but it's forming a hydride.
Exactly. Think about the nature of the product. EH, sodium hydride, is an ionic compound.
Na plus H.
Precisely. Sodium is a highly electropositive metal, and in NaH, it forms a positive ion, Na plus A, while hydrogen forms a negative ion, H, the hydride ion. This formation of ions explicitly indicates that electron transfer has occurred.
Ah, electrons moved.
Yes. Sodium has effectively lost an electron to hydrogen. So, from the perspective of electron transfer, sodium is oxidized, it loses electrons, and hydrogen is reduced, it gains electrons.
Okay, that makes sense. Loss is oxidation, gain is reduction.
This problem serves as a perfect bridge to our next, more universal definition of redox reactions, which focuses directly on electron movement. It's a beautiful example of how a deeper understanding clarifies what seems tricky on the surface.
The electron transfer perspective. A deeper understanding.
That's a profound shift in perspective, moving from observable changes like adding oxygen to the fundamental particle driving them, the electron. The NEET example truly underlines that we need a more universal definition, one that works even when oxygen or hydrogen aren't overtly involved. Our sources suggest this fundamental shift to understanding redox through electron transfer. How does this reframe oxidation and reduction for us?
Precisely. The classical definitions, while foundational, are descriptive. They tell you what happened based on observation. The electron transfer perspective, however, reveals the underlying mechanism, why it happened. And for reactions that produce ionic compounds like NaCl or NaH, we can directly link those classical changes, adding an electronegative element or adding hydrogen to form a hydride, to the explicit movement of electrons.
So it explains the why.
Yes. Let's consider some key examples from your material. When metallic sodium reacts with chlorine gas to form sodium chloride,
NaCl.
or with oxygen to form sodium oxide, Na2O,
Right.
or even with sulfur to form sodium sulfide, Na2S. Classically, we'd say sodium is oxidized because it's adding an electronegative element, and the other nonmetal is reduced because it's adding electropositive sodium.
Okay, the classical view.
But when we look at the products, NaCl, Na2O, Na2S, we recognize them as ionic compounds. They exist as distinct ions.
Yeah.
Na plus LEL, Na plus 2O2, and Na plus 2S2.
Got it. Charges.
The presence of these definite charges implies a clear, actual transfer of electrons. This insight allows us to dissect the overall reaction into what we term half reactions.
Half reactions. Explain that.
Okay, let's use the formation of sodium chloride as our illustration. The complete reaction is 2Na solid plus Cl2 gas yields 2 NaCl solid. We can conceptually separate this into two processes.
Okay.
First, the sodium atoms are losing electrons. 2Na solid transforms into 2Na plus gaseous ions by releasing 2 electrons. This step, where electrons are lost, is precisely what we define as the oxidation half reaction.
Loss of electrons equals oxidation half.
Second, the chlorine molecules are gaining those very electrons. A Cl2 molecule combines with 2 electrons to form 2 Cl gaseous ions. This step, where electrons are gained, is defined as the reduction half reaction.
Gain of electrons equals reduction half. Okay.
And when you sum these two half reactions, the electrons on both sides cancel out, giving you the overall balanced reaction. It's like splitting the process in two.
Very clear. So how does this lead to new definitions?
This leads us to the formal definitions based on electron transfer, which are far more precise and universally applicable for your exams. Oxidation is definitively the loss of electrons by any chemical species. Simple as that.
Loss is oxidation. LEO.
Exactly. And reduction is definitively the gain of electrons by any chemical species.
Gain is reduction. GER. LEO, the line says GER.
That's a popular mnemonic, yes.
Yeah.
It says GER. Building on this, the agents involved are also redefined. An oxidizing agent, or oxidant, is the species that accepts electrons. It causes oxidation in another substance by taking electrons from it, and in doing so, the oxidizing agent itself gets reduced.
So the oxidant gets reduced. Makes sense.
Think of chlorine, oxygen, or sulfur. In our sodium examples, they are the electron acceptors, the oxidants.
Okay.
A reducing agent, or reductant, is the species that donates electrons. It causes reduction in another substance by giving electrons to it, and in doing so, the reducing agent itself gets oxidized.
And the reductant gets oxidized. Okay.
In those same reactions, sodium metal is the electron donor, the reductant.
Got it. Oxidant accepts electrons, gets reduced. Reductant donates electrons, gets oxidized.
What's critical to understand is that this electron transfer definition perfectly correlates with our earlier classical ideas. When magnesium adds oxygen, it's because oxygen, being highly electronegative, is pulling electrons away from magnesium. Magnesium loses electrons, and thus it's oxidized.
Right.
So this isn't a contradiction, but rather a deeper mechanistic explanation for the phenomena described classically. This is a vital conceptual leap for you.
That certainly makes things incredibly clear. The idea of electron transfer feels much more fundamental. Let's revisit problem 7.2 from our material, but now with this new understanding, justify that the reaction, 2NOS plus H2G, 2NOS, is indeed a redox change.
Let's confidently apply the electron transfer definition to this reaction.
Okay.
First, as we discussed, the compound formed, sodium hydride, NaH, is an ionic compound, represented as Na plus H solid.
The ionic nature is key.
It is. The very nature of this compound tells us that electrons have been completely transferred from sodium to hydrogen. Second, we can explicitly show this electron movement by breaking it down into half reactions. The oxidation half reaction involves sodium. 2Na solid transforms into 2Na plus gaseous ions by releasing 2 electrons. Here, sodium atoms are clearly losing electrons, LEO.
Sodium loses electrons.
Oxidized. The reduction half reaction involves hydrogen. The H2 gas molecule combines with 2 electrons to form 2 H gaseous ions. Here, hydrogen molecules are clearly gaining electrons. GER.
Hydrogen gains electrons. Reduced.
So the conclusion is undeniable. Since sodium is oxidized by losing electrons and hydrogen is reduced by gaining electrons, and these processes occur simultaneously, the overall reaction 2Na solid plus H2 gas yields 2Na solid is unequivocally a redox change. It's a perfect illustration of how this electron transfer perspective resolves ambiguities.
Excellent. Now that we deeply understand electron transfer, what happens when elements actively compete for these electrons? Our material delves into competitive electron transfer reactions. This sounds like an electron tug of war.
It is indeed an electron tug of war. And this concept is where the theoretical definitions beautifully translate into observable chemical behavior. It forms the foundation of many practical applications, especially in electrochemistry.
Linking to batteries and things.
Exactly. Competitive electron transfer is about which species possesses a stronger inherent tendency to either give up or accept electrons when placed in contact with another. Who wants the electrons more?
Okay.
Let's start with a classic and very illustrative demonstration often seen in labs, referenced as Figure 7.1 in your notes. If you place a clean zinc strip into an aqueous solution of copper nitrate.
Copper nitrate is blue, right? Because of Cu2 plus ions?
Precisely. You'll notice copper nitrate solution has that distinctive blue color due to the Cu2 plus ions. After some time, say an hour or so, you'll observe two remarkable changes. Firstly, the zinc strip becomes coated with a reddish metallic layer. This is elemental copper depositing from the solution.
So copper metal forms on the zinc.
Yes. Secondly, and equally striking, the vibrant blue color of the solution begins to fade and eventually disappears entirely.
The blue C2 plus ions are gone.
Exactly. They are being consumed. We can confirm the formation of colorless Zn2 plus ions by testing the solution afterwards.
Okay, so what's the reaction?
The reaction occurring here is simple. Zinc solid plus copper 2 ions aqueous yields zinc ions aqueous plus copper solid, ZnS plus Cu2 plus AuN2 plus Aq plus HuS.
Right.
In this reaction, zinc metal has spontaneously lost electrons to form Zn2 plus ions.
Zinc is oxidized.
Meaning zinc is oxidized. And because oxidation and reduction are always coupled, it's the copper ions that are accepting those electrons. So Cu plus ions are reduced by gaining electrons from the zinc to form elemental copper.
Copper ions reduced. Okay.
What's crucial is that the equilibrium for this specific reaction heavily favors the products. It essentially goes all the way to the right. Zinc wants to give electrons to copper ions more than copper wants to keep them.
Zinc wins the tug of war. That makes perfect sense. So if zinc is so good at giving up electrons to copper, what happens if we try the reverse? Putting copper into a zinc sulfate solution?
That's a very insightful question, and it's precisely how we test this competition. If you place a strip of metallic copper into a zinc sulfate solution, which is colorless, containing Zn2 plus ions,
what happens?
you will observe absolutely no visible reaction. Nothing.
Nothing at all?
Nothing. The solution's color remains unchanged, and if you test for the presence of copper ions, you won't find any detectable amount.
Why not?
This tells us a fundamental truth. The reverse reaction, where copper would lose electrons to zinc ions, is simply not favored. The equilibrium we discussed for the zinc-copper reaction lies strongly to the right. Zinc is a much stronger electron donor, a better reducing agent than copper. Copper can't displace zinc ions.
Okay, so zinc-copper in terms of giving electrons.
Exactly. Let's consider another compelling example of this competition, involving copper metal and silver nitrate solution, as shown in Figure 7.2.
Silver nitrate, AgNO3.
Yes. If you carefully place a copper strip into a solution of silver nitrate, which is colorless, containing Ag plus ions, you'll immediately begin to see changes.
What changes?
The solution will gradually develop a blue color.
Cu2 plus ions forming.
Correct. Unmistakably indicating the formation of Cu2 plus ions. Simultaneously, shiny silver metal will start to deposit directly onto the copper strip, like little crystals.
Cool. So silver metal forms.
The reaction is copper solid plus 2 silver ions aqueous yields. Copper ions aqueous plus 2 silver solid, Qs plus 2 Ag plus Cu2 plus Aq plus 2 Aq.
So copper loses electrons.
Copper is oxidized to C2 plus by losing electrons, and silver ions Ag plus 2 are reduced to solid silver by gaining those electrons. Just like with zinc and copper, the equilibrium for this reaction also strongly favors the products.
So copper is a better reducing agent than silver.
Yes, copper wins the electron tug of war against silver ions.
So we have Z and Q Ag in terms of electron donating tendency?
That's the order emerging. We see one metal clearly dominating another in electron transfer. Yeah. Is there ever a true draw or a more balanced competition?
Yeah. Is it always so one-sided?
That's an excellent point. And yes, there are reactions where the competition is more evenly matched. Consider the reaction of metallic cobalt placed in a nickel sulfate solution. Cobalt solid plus nickel second. Ions aqueous yield cobalt 2. Ions aqueous plus nickel solid. Cobalt plus Ni2 plus Aq plus Naq plus Niq. Notice the equilibrium arrows.
Okay, cobalt and nickel, what happens there?
When this reaction reaches equilibrium, if you perform chemical tests, you'll find that both nickel ions, Ni2+, and cobalt ions, CO2+, are present in significant moderate concentrations.
So it doesn't go fully one way?
Exactly.
Yeah.
What this signifies is that neither the reactants nor the products are overwhelmingly favored. Instead, it's a genuine, observable competition for electrons, resulting in a true equilibrium where all species coexist. Cobalt and nickel are much closer in their electron donating abilities.
Interesting.
This entire idea of metals competing for electron release, where some are more willing to give up electrons than others, is very analogous to how acids compete for protons, strong acids versus weak acids.
Ah, like acid strength.
Similar idea. This analogy allows us to systematically develop what is known as the metal activity series, or the electrochemical series. From the experiments we've just discussed, we can deduce an order of electron-releasing tendency. Zinc is a stronger electron donor than copper, and copper is a stronger electron donor than silver. So the order of reducing power is ZnQ Ag.
That series sounds really important.
It is incredibly powerful, and you will delve much deeper into the comprehensive metal activity series and the full electrochemical series in your Class 12 electrochemistry studies.
Okay, something to look forward to.
What's truly profound about these competitive electron transfer reactions is that they form the very foundation for a class of devices we call galvanic cells. These are electrochemical cells where these spontaneous chemical reactions are ingeniously harnessed to produce electrical energy.
Like batteries.
Exactly like batteries. So understanding this competition is absolutely key to grasping how batteries and other electrochemical devices function, powering our world.
Oxidation number, the modern bookkeeping tool.
That's truly fascinating, observing how different metals engage in this electron competition. It directly leads to practical things like batteries. But what about those reactions where electrons aren't fully transferred, for instance, in compounds with covalent bonds? How do chemists precisely track these subtle electron shifts there, especially for competitive exams?
That's a critical question, and it points to a significant evolution in how chemists conceptualize redox. The electron transfer definition works perfectly for ionic compounds where the transfer is complete, like NaCl.
Sure. Full transfer.
However, for reactions involving covalent compounds where electrons are shared rather than fully given or taken, the picture becomes more nuanced. It's not a full transfer.
Your shared electrons, like in water.
Exactly. Take the formation of water from hydrogen and oxygen. 2H2 gas plus O2 gas yields 2H2O liquid. While we can imagine hydrogen atoms going from a neutral state in H2 to a slightly positive state in H2O, and oxygen from neutral O2 to a slightly negative state in H2O, suggesting an electron shift.
It's not Na plus Cl. It's shared.
Correct. It's not a complete transfer. The electrons are still technically shared within the covalent bonds.
Okay.
This challenge also applies to numerous other reactions involving covalent bonds. Consider hydrogen gas reacting with chlorine gas to form hydrogen chloride, HCl, or the chlorination of methane, CH4, to form carbon tetrachloride, CCl4, and HCl.
Lots of covalent examples.
In these scenarios, we need a consistent way to track these electron shifts, even without the formation of explicit ionic charges. We need a system.
So what's the system?
To solve this, chemists developed a practical and powerful bookkeeping tool called oxidation number, often used interchangeably with oxidation state.
Oxidation number, okay.
This concept allows us to track the apparent electron shifts in both ionic and covalent compounds systematically. The core assumption for calculation, and this is crucial for you, is that in a covalent bond, we hypothetically assume a complete transfer of electrons from the less electronegative atom to the more electronegative atom.
Assume complete transfer even if it's not real.
Exactly. It's a simplifying assumption, a convention, but it enables us to assign a numerical state to each element, making redox analysis much more tractable. It's for counting purposes.
Okay, counting tool.
Let's quickly re-examine those previous equations with assigned oxidation numbers to clarify this. For water formation, H2 starts at 0, O2 starts at 0. In water, H2O, hydrogen is assigned +1 and oxygen is -2.
Okay.
For hydrogen chloride, H2 is 0, Cl2 is 0, and HCl, hydrogen is +1, chlorine is -1. And for methane chlorination, in CH4, carbon is -4 and hydrogen is +1. In CCl4, carbon is +4 and chlorine is -1. Notice how we assign these numbers representing assumed charges. Remember, this complete electron transfer is solely a bookkeeping device, but it immensely simplifies the description and, most importantly, the balancing of complex redox reactions, which are vital for your competitive exams.
So it helps with balancing. That's key.
So formally, the oxidation number signifies the oxidation state of an element within a compound. It's determined by a specific set of rules, formulated on the basis that, for calculation purposes, an electron pair in a covalent bond is considered to belong entirely to the more electronegative element.
Okay, rules. Let's hear them. These sound important.
Now let's go through these indispensable rules for assigning oxidation numbers. Mastering each one is absolutely critical for solving problems in this chapter. I'll explain each rule methodically, providing key examples. Take notes if you need to. Rule 1. Elements in their free or uncombined state. This is the simplest rule. Any atom existing as an uncombined element has an oxidation number of 0.
0 for elements, like Na metal or O2 gas.
Precisely. Think of H2, O2, Cl2, O3, ozone, P4, white phosphorus, S8, rhombic sulfur, or any pure metal like Nan, Mg, Al. Their oxidation number is always 0.
Got it. Rule 1, elements equal 0.
Rule 2, monoatomic ions. For an ion composed of just one atom, its oxidation number is simply equal to the charge on the ion.
So Na plus is +1, Cl is -1.
Exactly. Na plus is +1, Mg2 plus is +2, F3 plus is +3, Cl is -1, and O2 is -2. A crucial tip for your exams, in all their compounds, alkali metals, group 1 elements like Li, M, K, consistently have an oxidation number of +1.
Group 1 always +2.
And aluminium, group 2 elements like B, M, G, K, consistently have an oxidation number of +2.
Group 2 always +2.
And aluminium, group 13, is generally considered to have an oxidation number of +3 in its compound.
I'll usually +3. Good shortcuts.
Rule 3, oxygen. This rule has important exceptions that you must commit to memory for competitive exams. Generally, the oxidation number of oxygen in most compounds is -2.
Usually -2, like in water or CO2.
Yes. However, be aware of these exceptions. First, in peroxides like H2O2 or Na2O2, where oxygen atoms are directly bonded, O-O linkage, each oxygen atom is -1.
Peroxides O is -1, like H2O2. Got it.
Second, in superoxides like KO2 or RbO2, each oxygen atom exhibits a fractional oxidation number of metic.
Superoxides O is -12. Okay, that's unusual.
It is. The third and relatively rarer exception occurs when oxygen is bonded to fluorine, the most electronegative element. In compounds such as oxygen difluoride, OF2, and dioxygen difluoride, O2F2, oxygen actually displays positive oxidation numbers, +2 in OF2 and +1 in O2F2.
Okay, memorize these oxygen exceptions.
Yeah.
-1 in peroxide, -12 in superoxide, positive with F.
Rule 4, hydrogen. Generally, the oxidation number of hydrogen is +1.
Usually +1, like in HCl or H2O.
Correct. The critical exception here is when hydrogen is bonded to metals in binary compounds, known as metal hydrides, such as LaH, NaH, or KH2.
Ah, like the NaH example earlier.
Exactly. In these compounds, hydrogen, being more electronegative than the alkali or alkaline earth metal, gains an electron, and its oxidation number is -1.
H is -1 in metal hydrides.
Okay. Rule 5, fluorine and other halogens. Fluorine, being the most electronegative element across the entire periodic table, always has an oxidation number of -1 in all its compounds. This is an unbreakable rule.
Fluorine always -1. No exception.
No exceptions for fluorine. Other halogens, chlorine, bromine, and iodine, also have an oxidation number of -1 when they are present as halide ions in binary compounds. Example, NaCl, KBr.
Viol, Br. Usually -1 is halides.
Usually. However, unlike fluorine, chlorine, bromine, and iodine can exhibit a range of positive oxidation numbers when they are combined with oxygen.
Oh, like in chlorates or perchlorates?
Precisely. You'll see this in oxoacids like HClO4, where chlorine is +7, or in oxoanions like ClO3, where chlorine is +5.
Okay, so ClBr. I can be positive with oxygen.
Rule 6, sum of oxidation numbers. This rule is paramount for calculating unknown oxidation numbers. For a neutral compound, the algebraic sum of the oxidation numbers of all the atoms present in the compound must always be 0.
Sum equals 0 for neutral molecules.
And for a polyatomic ion, the algebraic sum of all the oxidation numbers of the atoms within the ion must be equal to the net charge on that ion.
Sum equals the charge for ions. Like CO32, sum is -2.
Perfect. An important point. If a molecular ion contains multiple atoms of the same element, like in Na2S2O3, sodium thiosulfate, or Cr2O72, dichromate ion, the calculated oxidation number for that element is often an average oxidation state.
An average. Can that be a fraction?
It can sometimes result in fractional values, which we will address in detail shortly, as they represent a unique scenario that often confuses students.
Okay, average and fractions coming up.
General trends you should remember. Metallic elements will invariably have positive oxidation numbers in their compounds because they inherently tend to lose electrons.
Metals positive.
Non-metallic elements, on the other hand, are more versatile and can exhibit both positive and negative oxidation numbers, depending on what they're bonded to.
Non-metals positive or negative.
Transition elements are particularly noteworthy for displaying a wide array of multiple positive oxidation states, which makes their chemistry rich and complex.
Transition metals have lots of possibilities.
A useful rule for representative elements, Skal block and P block, is that their highest oxidation number often correlates with their group number. For group 1 and 2 elements, it's simply their group number. For other groups, 13, 17, based on the modern periodic table, it's often their group number minus 10.
Okay, like chlorine in group 17, highest is plus 7, 1710.
Exactly, like in HClO4. As you move across the third period, from sodium to chlorine, the highest possible oxidation number generally increases from plus 1 to plus 7.
Got it. Final point on terms.
A final clarification on terminology. Oxidation number and oxidation state are largely interchangeable terms in competitive exams. For example, when we say carbon in CO2 is in the plus 4 oxidation state, we also mean its oxidation number is plus 4. They refer to the same concept.
Oxidation number, oxidation state.
Good. This brings us to a very useful naming convention for metals, particularly transition metals, known as Stock notation, developed by the German chemist Alfred Stock.
Stock notation, what's that?
This notation expresses the oxidation number of a metal by placing a Roman numeral in parentheses immediately after the symbol of the metal in the chemical formula. This is extremely important for correctly naming inorganic compounds in your competitive exams.
Roman numerals for the oxidation state.
Okay, for example, Orous chloride, where gold has a plus 1 oxidation state, is systematically written as AAClL. In contrast, auric chloride with gold in a plus 3 state is OICl.
OC and OCl3. Clear.
Similarly, stannous chloride, tin in plus 2, is SNiCl2, and stannichloride, tin in plus 4, is SNIVCl4.
SNiCl2 and SNIVCl4.
Got it. This notation precisely indicates the specific oxidation state of the metal, which also helps in clearly identifying whether a species is in an oxidized or reduced form. For instance, Hg2RaCl2 is considered the reduced form compared to HgDrCl2.
That's a remarkably clear and detailed set of rules for assigning oxidation numbers. Let's put stock notation into practice with problem 7.3 from our material. Represent the following compounds using stock notation: HeLCO4, Tl2O, FeO, Ft2O3, QI, CuO, MnO, and MnO2.
Excellent. Let's apply these rules systematically to each compound. Remember, the goal is to find the metal's oxidation state and represent it with Roman numerals.
Okay, first one, HAlCl4.
First, for HrCl4, we know hydrogen typically has an oxidation number of plus 1, and chlorine, as a halide not bonded to oxygen or fluorine here, is minus 1. There are 4 chlorine atoms contributing a total of minus 4.
Okay, H is plus 1, 4Cl is 9 to 4.
The compound is neutral, so plus 1 from H plus NaO's oxidation state, plus minus 4 from 4Cl CO. Solving this, O must be plus 3.
Plus 1 plus O, 4, each OR does 0.
That's so in stock notation is HRORCCl4. Take a moment to see that.
Thoth3Cl4. Got it. What about Tl2O?
For Tl2O, oxygen is generally -2. Since the compound is neutral and there are 2 thallium Tl atoms.
2 Tl balance out -2.
Right, the 2 thallium atoms must collectively provide a plus 2 charge to balance the -2 from oxygen. Therefore, each Tl atom must be plus 1.
Tl is plus 1.
In stock notation, this is Tl2.
IL2IL. Makes sense. FeO next.
For FeO, oxygen is -2. For the compound to be neutral, iron F must be plus 2. Simple enough, Famil 2.
FeO easy. And Fe2O3.
Now, F2O3, oxygen is -2. With 3 oxygen atoms, the total negative charge is -6.
3 times -2 is -6.
For neutrality, the 2 iron atoms must collectively contribute +6, so 2 equals +6, which means each Fe atom is +3.
FeO.
Iodine, being a halogen not bonded to oxygen or fluorine, has an oxidation number of -1.
PeVO3 is -1.
Therefore, to balance this for a neutral compound, copper C must be +1, so this is Qi.
Helium CuO.
For CO, oxygen is -2. For neutrality, copper, Cu, must be +2. This is simply QiO. Okay.
MnO. For MnO, oxygen is -2, plus manganese, Mn must be +2, so MnIO.
MnIO. Finally, MnO2.
And for MnO2, oxygen is -2. With 2 oxygen atoms, the total negative charge is -4. So manganese, Mn must be +4. This is MnIAO2.
MnIO2. Great. This exercise is crucial for your competitive exams, as you'll often need to identify oxidation states quickly.
Absolutely. Practice makes perfect with these.
That was a great practical session. Now, with oxidation numbers firmly in hand, how do we redefine oxidation, reduction, and the roles of redox agents using this more modern quantitative concept? This seems more powerful than the classical way.
It is indeed more powerful and universal. With oxidation numbers, we now possess a more encompassing and mathematically traceable definition for redox processes, applicable seamlessly to both ionic and covalent compounds. This is a significant step forward. Okay, so the new definitions.
Oxidation is defined simply as an increase in the oxidation number of an element within a given substance. If an element's oxidation number goes up, it has been oxidized.
Oxidation Increase in oxidation number.
Reduction is defined as a decrease in the oxidation number of an element within a given substance. If an element's oxidation number goes down, it has been reduced.
Reduction, decrease in oxidation number.
An oxidizing agent or oxidant is a reagent that causes an increase in the oxidation number of an element in another substance. In doing so, the oxidizing agent itself undergoes a decrease in its own oxidation number. It gets reduced.
Oxidant causes oxidation, gets reduced, its on end decreases.
A reducing agent or reductant is a reagent that causes a lowering of the oxidation number of an element in another substance. Conversely, the reducing agent itself undergoes an increase in its own oxidation number. It gets oxidized.
Reductant causes reduction, gets oxidized, its on end increases.
Okay. And finally, redox reactions are unequivocally reactions that involve a change in the oxidation number of the interacting species. If you can identify even one element changing its oxidation number from reactants to products, then it's a redox reaction.
Change in on end means redox. This is the most precise definition you'll use in competitive exams.
Absolutely. This is the definition to rely on.
Perfectly clear. Let's apply this definition directly with problem 7.4. Justify the reaction. 2Cu2S plus Cu2SS plus SO2G is a redox reaction. Then identify the species that are oxidized, reduced, and which act as the oxidant and reductant.
This problem is an excellent way to consolidate your understanding of oxidation numbers and their application. Let's tackle it systematically, step by step.
Okay.
First, our primary step is to assign oxidation numbers to every element in all the species involved in the reaction.
Right, Cu2O.
For Cu2O, oxygen is typically -2. Since there are 2 copper atoms and the compound is neutral, each copper atom must be +1.
Q is +1 in Cu2O. Okay, C2S.
For C2S, sulfur in sulfides is generally -2. Similarly, with 2 copper atoms balancing it, each copper atom here must also be +1.
Q is +1 in C2S2, right?
Right.
Product side, Q.
For QS, this is elemental copper in its uncombined state, so its oxidation number is 0.
Q is 0 in SO2.
For SO2G, oxygen is -2. With 2 oxygen atoms, the total negative charge is -4. For the molecule to be neutral, sulfur must be +4.
S is +4 in SO2. Okay, we have all the numbers.
So we've identified the oxidation states. Copper starts at +1 in both reactants and goes to 0. Sulfur starts at -2 in C2S and goes to +4 in SO2. Oxygen stays at -2.
Now let's pinpoint the changes based on the new definitions.
Indeed. Second, let's identify which elements are changing their oxidation numbers and how. Looking at copper, it changes from +1 in C2O and C2S to 0 in elemental Q. A change from +1 to 0 represents a decrease in oxidation number.
Decrease means?
Reduction, so copper is reduced.
Copper reduced, okay?
Yeah.
Sulfur.
Next, let's examine sulfur. It changes from -2 in C2S to +4 in SO2. A change from -2 to +4 represents an increase in oxidation number.
Increase means?
Oxidation. So sulfur is oxidized.
Sulfur oxidized. So if both oxidation and reduction are happening.
Precisely. Conclusion 1. Since we observe that copper is being reduced, on-N decreases, and sulfur is simultaneously being oxidized, on-N increases in this reaction, it unequivocally fits the definition of a redox reaction.
Okay, it's redox. Now, the agents. Who is the oxidant? Who is the reductant?
Now for conclusion 2. Identifying the agents. Remember the rule. The oxidant gets reduced and the reductant gets oxidized. We identified that copper, specifically the Qi in both Cu2O and C2S, is reduced. Its on-N decreases from +1 to 0.
Right, copper is reduced.
Which substance caused sulfur's oxidation number to increase? It was the copper species accepting electrons. Both C2O and C2S contain Qi, which gets reduced. However, the oxidant is typically considered the entire compound containing the element being reduced. So Cu2O is acting as the oxidant. It accepts electrons from sulfur, causing sulfur's oxidation.
Okay, Cu2O is the oxidant. What's the reductant?
Now for the reductant. We identified that sulfur, specifically the S in Cu2S, is oxidized. Its on-N increases from -2 to +4. Which substance caused copper's oxidation number to decrease by donating electrons? It was the sulfur in C2S.
The sulfur donated electrons.
Yes. Therefore, the sulfur of C2S, or you could say C2S itself, acts as the reductant because it contains the element being oxidized, acts as the reductant. It donates electrons, causing the reduction of copper in both C2S itself and C2O. This is a great example of a reaction sometimes called autoreduction or self-reduction, often seen in metallurgy.
That's a truly comprehensive breakdown. You mentioned earlier that sometimes we encounter fractional oxidation numbers and that it can seem like a paradox. How do we make sense of that without literally splitting electrons?
That's an insightful observation, and it's a common point of confusion for students. The idea of a fractional oxidation number can indeed seem counterintuitive because you're right, we know electrons are discrete particles and aren't transferred in fractions.
What's going on?
However, it's not a true paradox. It's a consequence of the bookkeeping definition we apply and the complex reality of molecular structure. The crucial insight here is that when you calculate a fractional oxidation number for an element, it is almost always an average oxidation state.
An average, meaning?
Meaning the element in question is actually present in different, distinct whole number oxidation states within that very molecule or ion. The true picture, the reality, is revealed by studying the molecule's precise structural arrangement.
Ah, so the structure tells the real story.
Exactly. Let's illustrate this with some key examples provided in your source material, which also includes their structures. Consider C3O2, known as carbon suboxide. If you calculate the average oxidation number for carbon using our rules, 2O equals plus 4, so 3C equals plus 4, average C plus 43.
Plus 43, a fraction.
Right. But when you look at its actual linear structure, OACCCO, with the asterisk on the middle carbon, you see something fascinating. The two carbon atoms at the ends are each in a +2 oxidation state, while the central carbon atom is in a 0 oxidation state.
So +2, 0 +2.
Yes, and the average of +2 + 0 + +2 divided by 3 perfectly gives you +43, even though individual carbons have whole number oxidation states.
Okay, the average makes sense of the fraction. Another example.
Another example is Br308, tribrom coctoxide. The calculated average oxidation number for bromine here is +163. 8O equals the next 16, so 3Br plus 16. Average Br plus 163. Again, a fraction.
Plus 163.
Okay.
What's the structure show?
Its structure reveals that the two bromine atoms at the ends are each in a +6 oxidation state, and the middle bromine atom is in a +4 oxidation state.
6 + 4 + 6.
And the average of +6 + +4 + 6 divided by 3 is indeed +163.
Wow, okay, one more.
And then there's a S462, the tetrathionate ion. If you calculate the average oxidation number for sulfur, 6O in -12, overall charge -2, so 4S a +10, average S plus 104 plus 2.5.
Plus 2.5.
Looking at its structure, you'll find that the two sulfur atoms at the extreme ends are each in a +5 oxidation state, while the two central sulfur atoms, bonded only to each other, are each in a 0 oxidation state.
So +5, 0, 0 +5.
Correct. And the average +5 + 0 + 0 + +5 gives you a +104 or +2.5.
The fractions come from averaging different whole number states within the molecule.
Precisely. This phenomenon of average oxidation numbers is also common in mixed oxides, such as F3O4, Mn3O4, and Pb3O4. These aren't single compounds with a uniform oxidation state for the metal. Rather, they are essentially stoichiometric mixtures of different oxides of the same metal.
Like F3O4 being FeO and F2O3.
Exactly. F3O4 is effectively a combination of FeO, Fe +2, and FeO3, Fe +3. Here, iron exists in both +2 and +3 oxidation states, which, when averaged across the whole formula, 1F +2 +2 +3 of 3, 4 atoms plus 83, leads to an average fractional value.
Okay. Are there ever real fractional states?
While very rare, it's worth noting that
Indeed. Categorizing redox reactions helps you recognize patterns, predict reactivity, and solve problems efficiently. It gives you a framework. Redox reactions can generally be grouped into 4 main types: combination reactions, decomposition reactions, displacement reactions, and a particularly special and intriguing category called disproportionation reactions.
Okay, 4 types. Let's start with neuronation.
Let's start with 1, combination reactions. These reactions follow the general form, A plus B, AC.
Simple combination.
The fundamental condition for a combination reaction to be classified as a redox reaction is that either substance A or substance B, or crucially, both A and B, must initially be in their elemental form.
Elemental form, meaning oxidation state 0.
Correct. Their starting oxidation state is 0. When they combine to form a compound, their oxidation numbers will invariably change, making it a redox process. A significant number of everyday processes, including all combustion reactions that involve elemental dioxygen, O2, fall into this category. Let's look at some illustrative examples. When solid carbon combines with oxygen gas to form carbon dioxide, C is plus O2G. Here, both carbon 0 and oxygen start as elements. In CO2, carbon goes to +4 and oxygen to -2. Clear redox combination.
Okay.
Another example, magnesium solid reacting with nitrogen gas to form magnesium nitrate. 3MgS plus N2G, Mg3N2s. Both magnesium 0 and nitrogen 2 start elemental. In Mg3N2, Mg is +2 and N is -3. Again, a redox combination.
Right.
Even in the combustion of methane, CH4G plus 2O2G plus 2H2L, although methane isn't an elemental substance, oxygen is O2 state 0. Since an elemental substance undergoes a change in its oxidation state and combines, this is categorized as a redox combination reaction.
So the key is at least one reactant starting as an element of ON0. Got it.
Right.
What about the opposite decomposition reactions?
Next, we have 2 decomposition reactions. These are essentially the reverse of combination reactions.
Yeah.
A single compound breaks down into 2 or more simpler components, C8 plus B.
Breaking down.
For a decomposition reaction to be classified as a redox reaction, at least one of the components formed must be in the elemental state. This is crucial because it guarantees a change in oxidation number from a compound, non-zero ON, to an element, 0 ON.
Okay, so at least one product must be elemental.
Exactly. It's an important distinction for your competitive exams. Not all decomposition reactions are redox reactions.
Give me an example of a non-redox one.
For instance, the decomposition of calcium carbonate upon heating, CaCO3s plus CO2G.
Yeah.
If you analyze the oxidation states, K3 is plus 2, C is plus 4, O is -2 in all compounds involved. No element changes its oxidation state.
No change in ion, so not 2 redox.
Right. Now let's look at some true redox decomposition examples. The electrolysis of water.
Yeah.
2H2G plus O2G. Here, water breaks down into elemental hydrogen and 0 in oxygen. Hydrogen changes from +1 to 0 and oxygen from -2 to 0. This is undeniably a redox decomposition.
H2 and O2 formed, both elemental.
Another common one, the decomposition of sodium hydride, 2NES plus HUG. Sodium hydride decomposes into elemental sodium, 0, and hydrogen gas. Sodium changes from +1 to 0, and hydrogen from -1 to 0. Also, redox decomposition.
NEA and H2 formed, redox.
Finally, the decomposition of potassium chlorate upon heating, 2KClO3s plus 3O2G. Here, potassium chlorate breaks down to potassium chloride and elemental oxygen, O2 state 0.
Yeah.
Oxygen changes from -2 to 0. Interestingly, chlorine also changes here, from +5 in KCl3 to -1 in KCl. Since an element O is formed and ONs change, it's redox decomposition.
That distinction between decomposition being redox or not is really important for exam questions. Our third category is displacement reactions. How are they defined, and what types do we typically encounter?
Moving on to 3. Displacement reactions. In a displacement reaction, an ion or an atom in a compound is replaced by an ion or an atom of another element. The general schematic is often represented as X plus YZ, XE plus Y. Element X displaces element Y from compound YZ.
X kicks Y out.
Essentially, yes. These reactions broadly fall into 2 key subcategories: metal displacement and non-metal displacement.
Okay, metal displacement first.
Metal displacement reactions. In these reactions, a more reactive metal displaces a less reactive metal from its compound. We touched upon this when discussing competitive electron transfer.
Like Zn displacing C2 plus A.
Exactly that example. Copper sulfate aqueous solution plus zinc solid yields copper solid plus zinc sulfate aqueous solution. ZSO4 and copia 2 plus ZNS ACS plus ZnSO4A. Here, zinc metal displaces copper. Zinc is a more reactive metal and a stronger reducing agent than copper.
Okay.
Uses.
These reactions are profoundly relevant and find extensive practical applications, particularly in metallurgical processes, where pure metals are extracted from their ores using a more reactive metal as a reducing agent.
Like getting metals from rocks.
Yes. Other important industrial examples include vanadium pentoxide solid reacting with calcium solid to yield elemental vanadium, V2O5 plus 5CS2V plus 5 COs. Calcium displaces vanadium.
Titanium tetrachloride liquid reacting with magnesium solid to yield elemental titanium. TiCl4 plus 2MgS plus 2MgCl2. Magnesium displaces titanium.
Right.
Chromium oxide solid reacting with aluminum solid to yield elemental chromium. Cr2O3 plus 2Al plus 2CO2. Aluminium displaces chromium. Another thermite-type reaction.
The principle is always the same.
The underlying principle is consistently this. The reducing metal, the one doing the displacing X, must inherently be a better reducing agent, meaning it has a greater intrinsic capability to lose electrons than the metal it is displacing Y. The more reactive metal wins.
So it's always about the stronger reducing agent winning the electron tug of war. What about non-metal displacement? Do we see similar reactivity series there?
Excellent point. Yes, similar reactivity principles apply to B, non-metal displacement reactions. This category primarily includes hydrogen displacement and halogen displacement.
Hydrogen displacement first, kicking out H.
Let's delve into hydrogen displacement first. This involves certain metals displacing hydrogen from either water or acids. The reactivity varies greatly.
How so?
Highly reactive metals, specifically all alkali metals like Na, Ka, and some alkaline earth metals like Ka, Sun, Ba, are exceptionally strong reductants. They are so reactive that they can readily displace hydrogen even from cold water.
Like sodium and water fizzing.
Exactly, 2NF plus 2H2L plus H2G. That fizzing is the hydrogen gas. Similarly, calcium solid reacts with cold water. Calcan plus 2H2OL plus H2G.
Okay, very reactive metals use cold water. Less reactive ones.
Less active metals. Metals such as magnesium and iron are not reactive enough to displace hydrogen from cold water. Instead, they require higher energy input and react with steam to produce dihydrogen gas. For instance, MgS plus 2H2S plus 2H2S plus H2G, and iron reacting with steam. 2FSS plus 3H2O steam plus 3H2G. Steam needed for MgFS. Okay, what about acids? Displacement from acids. Many metals, including those that don't react with cold water or even steam, like zinc, cadmium, tin, are still potent enough to displace hydrogen from acids. This method is, in fact, commonly employed for the laboratory preparation of H2 gas.
Acid plus metal salt plus H2?
Typically, yes. Examples include ZNS plus 2HClAq plus 2HClAq plus H2G, MgS plus 2HClAq plus H2G. Does the speed differ?
Yes, in these reactions, the reactivity of the metal is directly reflected in the rate of hydrogen gas evolution. Magnesium is the most reactive, evolving hydrogen fastest, while iron is typically the slowest among these. It's also important to note that very less active metals, such as silver, Ag, and gold, which are often found uncombined in nature.
Scalable metals.
They do not react even with strong acids like hydrochloric acid to displace hydrogen. They don't want to give up electrons easily enough.
Okay, so a reactivity series for hydrogen displacement too. Now, halogen displacement. Now, let's consider halogen displacement reactions. Just as we have an activity series for metals based on their reducing power, tendency to lose electrons, there's a corresponding activity series for halogens based on their oxidizing power, tendency to gain electrons.
Oxidizing power for halogens.
Okay. The oxidizing power of halogens consistently decreases as you move down group 17 of the periodic table, from fluorine to iodine. So the order is F2Cl2Br2I2.
Chlorine is the strongest oxidant.
By far. Fluorine is so incredibly reactive it can even displace oxygen from water itself. 2H2OL plus 2F2G, 4HFAQ plus O2G. This extreme reactivity means that displacement reactions involving other halides using fluorine are generally not carried out in aqueous solutions.
F2 is too strong for water reactions.
No.
Okay, what about chlorine?
Chlorine, however, can readily displace both bromide, Br, and iodide in an aqueous solution because Cl2 is a stronger oxidant than Br2 and I2.
So Cl2 can kick out Br and I.
Yes. For example, Cl2G plus 2KBr, AQ plus 2KClAq plus Br2L, or written ionically, Cl2G plus 2BrNQ plus Br2 plus Br2L. Similarly for iodide, Cl2G plus 2AEQ is 2KClAq plus I2S, or ionically, Cl2G plus 2Lq plus I2S. Nice uses for this. These reactions are immensely useful in the laboratory. Since bromine, brownish, and iodine, violet in organic layer, are colored and dissolve well in organic solvents like carbon tetrachloride or dichloromethane, these reactions form the basis of the crucial layer test, used to identify the presence of Br and I ions in qualitative analysis. You shake the aqueous solution with the organic solvent after adding chlorine water.
Ah, the layer test. Yes. Can bromine displace iodide?
Yes, following the reactivity series Cl2Br2I2. Bromine liquid can also displace iodide ions in solution. Br2L plus 2 is my NAQ plus I2S.
Makes sense. Industrial relevance.
These halogen displacement reactions also have direct industrial applications. The recovery of halogens from their halide ions typically involves an oxidation process, essentially 2X2 plus 2E. You might use a stronger halogen or electrolysis.
But not for fluorine.
Right. It's important to remember that due to fluorine's unparalleled oxidizing power, it wants electrons the most. There is no chemical means to convert fluoride ions F back to elemental fluorine, F2. You can't find a chemical strong enough to take electrons from fluoride. The only way to achieve this is electrolytically, forcing the electrons off.
Only electrolysis for F2 production. Got it.
That's a vital distinction to remember for your exams.
That's a comprehensive overview of displacement reactions. Finally, we have the fourth type, disproportionation reactions. This sounds particularly unique in element acting as both an oxidant and a reductant simultaneously. in the same reaction.
Indeed. 4. Disproportionation reactions are a very special and intriguing class of redox reactions. It sounds odd, but it happens. In a disproportionation reaction, a single element, initially present in one specific oxidation state, is simultaneously oxidized to a higher oxidation state and reduced to a lower oxidation state.
So the same element goes both up and down in oxidation state.
Exactly. This means the same element is acting as both the oxidizing agent and the reducing agent for itself. It's reacting with itself, in a sense.
Wow. What allows that to happen?
The crucial condition for such a reaction to occur is that the reacting substance must contain an element capable of existing in at least 3 different oxidation states. Furthermore, the element in the reacting substance must be in an intermediate oxidation state among those possibilities.
Must be in the middle.
Yes. When it disproportionates, it forms products where that element now exists in both a higher oxidation state and a lower oxidation state than it started.
Okay. Example.
The classic and most commonly encountered example, frequently seen in chemistry labs, is the decomposition of hydrogen peroxide.
H2O2.
H2O2, HW, plus O2.
H2O2 decomposition.
Let's assign oxidation numbers. In H2O2, oxygen is in the -1 oxidation state. Remember, peroxide exception.
Yes. O is a -1 in peroxides.
This is an intermediate state for oxygen, which can exist commonly as 0 in O2 or -2 in water and most oxides. In the products, oxygen appears in H2O, where its oxidation state is a lower state, and in elemental O2, where its oxidation state is 0, a higher state.
So O goes from -1 down to -2 A and D up to 0.
Precisely. So oxygen in H2O2 is simultaneously reduced to -2 and oxidized to 0. This is a perfect example of disproportionation.
Okay. Other examples?
Other common examples of disproportionation reactions, particularly in alkaline mediums, basic solutions, include phosphorus, P4, starting at 0, elemental state, disproportionate to -3 in phosphine pH3, and +1 in hypophosphite ion H2PO2. The reaction is complex, P4 plus 3OH plus 3H2O, pH3 plus 3H2PO2.
P goes from 0 to -3 and +1.
Okay.
Sulfur.
Sulfur S8, also starting at 0, disproportionate to alkali to -2 in sulfite ion S2 and +2 in thiosulfate ion S2O32.
Yep.
S8 plus 12OH was 4S2 plus 2O32 plus 6H2O.
S goes from 0 to -2 and +2. Chlorine.
Chlorine, Cl2, starting at 0, disproportionate in cold dilute alkali to -1 in claret ion, Cl and +1 in hypochlorite ion, ClO. Cl2 plus 2OH, Cl plus Cleo plus H2O.
Cl goes from 0 to -1 and +1. You mentioned bleach.
Yes, this specific reaction, where chlorine reacts with hydroxide ions, is industrially significant because it describes the formation of common household bleaching agents, as the hypochlorite ion, ClO, is a powerful oxidizing agent used to remove color from stains.
Ah, so bleach making is disproportionation.
Part of it, yes. It's important to note a key exception among halogens. While bromine and iodine also exhibit disproportionation like chlorine, though reactions might differ slightly, fluorine shows a distinct deviation when reacting with alkali.
Fluorine again, what does it do?
For example, fluorine gas reacting with hydroxide ions yields fluoride ions, F, oxygen to fluoride OF2, and water, 2F2G plus 2OHAQ, plus OF2G plus H2OL.
Okay, what are the oxidation states here?
Here, fluorine itself is not disproportionate. Its oxidation state changes from 0 in F2 to only -1 in F. It only gets reduced.
Only reduced. But something must be oxidized.
Good question. Look at the oxygen. It starts at -2 in OH and goes to +2 in OF2. Oxygen gets oxidized by fluorine here.
Ah, oxygen gets oxidized, not fluorine. Why can't fluorine disproportionate?
Because fluorine cannot exhibit any positive oxidation state. Remember Rule 5. It's the most electronegative element. It can only go down from 0 to -1. It cannot be simultaneously oxidized, go up, and reduced, go down.
Because it can't go up. That makes sense.
Therefore, among the halogens, fluorine stands out as the one that does not show disproportionation tendency. This is a vital distinction to remember for your exams.
That's a truly clear breakdown of the types, and disproportionation is particularly interesting because it defies our initial intuition about an element's role. Let's tackle problem 7.5, which asks, which of the following species do not show disproportionation reaction and why? ClO, ClO2, ClO3, and ClO4. Also write reactions for each of the species that disproportionates.
This is a classic question that tests your understanding of oxidation states and the conditions for disproportionation. We'll approach this by first determining the oxidation state of chlorine in each oxoanion and then evaluating if it's an intermediate state.
Okay, step 1. Find the oxidation states.
First, let's assign the oxidation state of chlorine in each species. For ClO, hypochlorite ion, oxygen is -2, overall charge -1. So Cl plus -2 = 1. Chlorine is +1.
ClO is +1, okay.
For ClO2 chloride ion, 2 oxygen atoms equals 4. Overall charge made of 1, so Cl plus minus 1, chlorine is plus 3.
ClO2 is plus 3.
So ClO3, chloride ion, 3 oxygen atoms equals 6. Overall charge made of 1. So Cl plus minus is 1, chlorine is plus 5.
ClO3 is plus 5.
For ClO4 per chloride ion, 4 oxygen atoms equals 8. Overall charge made of 1. So ClO plus negative 8 equals 1, chlorine is plus 7.
ClO4 is plus 7, so we have chlorine at plus 1, plus 3, plus 5, and plus 7. Which one cannot disproportionate?
Now for the second part, remember that chlorine can exhibit a wide range of oxidation states, from -1 as in Cl all the way up to plus 7 as we just saw in ClO4.
Right, -1 to plus 7 is the range for ClO.
Given this range, the species that cannot disproportionate is ClO4, where chlorine is at plus 7.
Why?
Because chlorine in ClO4 is already in its highest possible oxidation state, plus 7. To disproportionate, an element must be able to go to both a higher and a lower oxidation state. Since chlorine is already at its maximum, it cannot be oxidized any further.
Can't go higher than plus 7.
Correct. Therefore, ClO4 can only act as an oxidizing agent, meaning it can get reduced, go down to plus 5, plus 3, plus 1, or -1, but it cannot act as a reducing agent. It cannot get oxidized further. This is a critical point to remember.
That makes perfect sense. It's reached its peak oxidation. Now, can you provide the disproportionation reactions for the others, the ones in intermediate states?
Absolutely. For the species with intermediate oxidation states, plus 1, plus 3, plus 5, we can write their disproportionation reactions. These often occur in pseudo conditions like acidic or basic media, but let's show the typical products. For CO, where ClO is plus 1, this is an intermediate state. Chlorine at plus 1 can be reduced, say, to -1, as in Cl, and simultaneously oxidized to a higher state, such as plus 5, as in ClO3. The balanced reaction often cited is 3ClO, 2Cl plus ClO3. This happens in hot alkali.
3ClO gives 2Cl and Cl3, plus 1 goes to -1 and plus 5.
Okay, for ClO2, where Cl is plus 3, this is also an intermediate state. Chlorine at plus 3 can be reduced, for example, to -1, as in Cl, and oxidized to a higher state, such as plus 5, as in ClO3. A possible balanced reaction is 6ClO2 plus 3H2O, 5ClO3 plus Cl plus 6H, let's show that one, 3ClO2, 2ClO3 plus Cl, check balancing, 3Cl minus 2Cl ball plus 1Cl, 6Cl minus C, so charge, and gets 3, and it 2, and it's 1, it gets, yes. Okay, 3ClO2 gives 2ClO3, and ClO plus 3 goes to plus 5, and it gets 1. For ClO3, where Cl is plus 5, this is another intermediate state. Chlorine at plus 5 can be reduced, say, to -1, as in Cl, and oxidized to its highest possible state, plus 7, as in ClO4. The balanced reaction is 4ClO3 plus 3ClO4. This often requires heating.
4ClO3 gives Cl and 3ClO4 plus 5 goes to -1 and plus 7. Great. Mastering these reactions will immensely help you on your competitive exams.
Yes, recognizing intermediate states is key.
Those are clear examples of disproportionation. Now, for a quick classification challenge from problem 7.6, suggest a scheme of classification for the following redox reactions. A, N2G plus O2G to NOG. B, 2PB and O2G plus 4NO2 plus O2G plus H2OL plus H2OL plus H2D. 2NO2G plus 2OHU plus NO3 plus H2OL.
Let's classify each of these reactions, justifying our choice by identifying the changes in oxidation numbers and the nature of the reactants and products.
Okay, N2 plus O2 minus 2NO.
For A, N2G plus O2G, ENOG. Here we have elemental nitrogen, N2ON0, and elemental oxygen, O2ON0, reacting together to form a single compound, nitric oxide, NON plus 2O2. Since two elemental substances combine to form a compound and oxidation states change, this is classified as a combination redox reaction.
Combination, got it. B, lead nitrate decomposing.
For B, 2PB NO32S plus 4NO2G plus O2G. In this reaction, a single compound lead nitrate is breaking down into multiple products. Crucially, one of the products formed is elemental oxygen, O2ON0.
Elemental product means?
It's a decomposition redox reaction. Oxygen changes from -2 in nitrate to 0 in O2. Nitrogen also changes from +5 to +4.
Decomposition. Okay, C, NaH plus H2O.
For C, NaS plus H2OL plus H2G. Here, hydrogen in AH is made of 1, and hydrogen in H2O is +1. They react to form elemental hydrogen H2O0. The hydride ion, from NaH, effectively displaces hydrogen from water.
Something is displacing something else.
Yes. This fits the definition of a displacement redox reaction, specifically non-metal hydrogen displacement. H1 is oxidized to H0, and H+1 is reduced to H0.
Displacement, right. And D, NO2 reacting with base.
For VO, 2NO2G plus 2HAQ plus NO3AQ plus H2OL. Let's quickly look at the oxidation state of nitrogen. In NO2, oxygen is -2, making nitrogen +4.
N is +4.
In the product NO2, nitrate ion, oxygen is -2, so nitrogen is +3.
N is +3.
In NO3, nitrate ion, oxygen is -2, so nitrogen is +5.
N is +5, so N goes from +4 to +3, A and D +5.
Exactly. Nitrogen in NO2 starts at an intermediate oxidation state of +4. It is simultaneously reduced to +3 in NO2 and oxidized to +5 in NO3.
That's the definition of.
Disproportionation redox reaction. Understanding these classifications is very valuable for your exams.
That covers our classification perfectly. But before we move on, problem 7.7 highlights a very interesting case. Why do these two seemingly similar reactions involving PB3O4 proceed so differently? One with HCl, the other with HNO3. PB3O4 plus 8HCl plus 8HCl2 plus 2 PBCl plus 4H2O. PB3O4 plus 4HNO3 and 2PbNO3 plus PbO2 plus 2H2O.
Yes, this is an excellent conceptual question, and it's a favorite for competitive exams because it probes your deeper understanding of mixed oxides and their reactivity. It looks like the same starting material, but the products are different.
Exactly. Why Cl2 with HCl but PbO2 with HNO3?
The crucial insight here is that PD3O4 is not a single compound with a uniform oxidation state for lead. It's not like Pb is just one state.
What is it then?
Instead, it is actually a stoichiometric mixture of 2 moles of lead oxide, PDO, and 1 mole of lead oxide, PbO2. So think of PB3O4 as effectively 2 PbO, PbO2. This fundamental fact explains their different reactivities.
So it's a mix of Pb plus 2 oxide and Pb plus 4 oxide.
Let's break down each reaction, starting with the PbO2 part. In PbO2, lead is in the +4 oxidation state. This is a higher oxidation state for lead, and its more stable oxidation state is typically +2. As seen in PbO and PbCl2.
Pb plus 4 wants to become Pb plus 2.
Because lead in PbO2 is in a higher oxidation state, it has a strong inherent tendency to gain electrons and get reduced to its more stable +2 state. This means PbO2 is capable of acting as an oxidant.
PbO2 is an oxidizing agent. Got it. Now with HCl.
Now let's analyze the reaction with HCl. PB3O4 plus 8HCl, a 3PbCl2 plus Cl2 plus 4H2O. This overall reaction can be understood as two simultaneous processes happening within the 2-PbO-PbO2 mixture.
Okay, first part, the PbO.
1. Reaction of PbO with HCl. The 2 moles of PbO present in PB3O4 are basic oxides. Basic oxides react with acids in a straightforward acid-base neutralization reaction without any change in oxidation states. So 2-PbO reacts with 4HCl to yield 2PbCl2 and 2H2O. Here, lead remains at +2, no redox involved in this part.
Acid plus base, most salt plus water. Simple. Second part, PbO2.
2. Reaction of PbO2 with HCl. This is where the redox chemistry occurs. The 1 mole of PbO2 acts as a powerful oxidant. It oxidizes the chloride ions, Cl, Rn, negative 1, from HCl into elemental chlorine, Cl2, Rn, angle 0.
Oxidizes Cl to Cl2.
Yes. In this process, lead in PbO2, which is at +4, is itself reduced to PbCl2, where lead is at +2. So PbO2 reacts with 4HCl to yield PbCl2, Cr2, and 2H2O. This is the distinct redox part.
Pb plus 4 becomes Pb plus 2, Cl1 becomes Cl0. Redox.
Therefore, when PB3O4 is 2-PbO2 reacts with HCl, you observe both an acid-base reaction from the PbO component and a redox reaction from the PbO2 component, leading to the characteristic evolution of elemental chlorine gas.
That's a clever distinction. So what happens with HNO3 then? If HCl can reduce PbO2, why does HNO3 yield PbO2 as a product? Why doesn't HNO3 reduce the PbO2 part?
That's the core of the problem. Now, consider the reaction with HNO3. PB3O4 plus 4HNO3 plus PbO2 plus 2H2O. Again, we have the 2 PbO and 1 PbO2 components.
Okay, PbO part first.
1. Reaction of PbO with HNO3. Similar to the HCl case, the basic oxide PbO reacts with nitric acid HNO3 in a simple acid-base neutralization. So 2-PbO reacts with 4HNO3 to yield 2PbNO3, and 2H2O. Lead remains at +2. No redox occurring here.
Acid-base again. Now the PbO2 part with HNO3. 2.
Reaction of PbO2 with HNO3. Here's the crucial difference. Nitric acid HNO3 itself is a very strong oxidizing agent. Remember, PbO2 is also an oxidant.
So you have two oxidants, PbO2 and HNO3.
Exactly. Because PbO2 is also an oxidant, Pb is already +4 and wants to be reduced. It is highly unlikely for one strong oxidizing agent, PbO2, to react in a redox manner with another strong oxidizing agent, HNO3. There's simply no easily oxidizable species in HNO3 for PbO2 to react with under these conditions. Neither wants to give electrons to the other.
So they don't react redox-wise.
Correct. Therefore, the PbO2 component of PB3O4 remains unreacted and appears directly as a product in the reaction mixture. It just sits there while the PbO part reacts.
Ah, that makes total sense now. HCl provides the CO, which can be oxidized by PbO2, but HNO3 doesn't have something easily oxidizable for PbO2.
Precisely. This elegantly explains why you observe PbO2 as a distinct product when Pb3O4 reacts with HNO3, but it is completely consumed, reduced to PbCl2, and leads to the production of Cl2 when reacting with HCl. The specific chemical nature of the acid matters. This is a subtle but important point for your competitive exams.
Mastering redox reaction balancing.
That was a fantastic real-world application of oxidation states, showcasing how deep your understanding needs to be for these exams. Now let's move to perhaps the most crucial skill for all competitive exams, mastering the art of balancing redox reactions. Our material outlines two primary systematic methods for this.
Absolutely. Balancing redox reactions is an indispensable skill for your JEE, NEET, and board exams. These reactions are often quite complex, and simple hit-and-trial methods are just not reliable or efficient, especially under exam pressure.
Definitely need a system.
Therefore, mastering systematic approaches is essential. We will meticulously discuss two primary methods: the oxidation number method and the half-reaction method, also famously known as the ion-electron method.
Two main methods. Which is better?
Both are highly effective, and honestly, your choice often comes down to individual preference and which feels more comfortable and efficient for you. Practice both.
Okay, let's start with method 1, oxidation number method. Can you walk us through with an example, problem 7.8? K2Cr2O7 plus NaDSO3 in acid solution, giving Cr3 plus and SO42.
All right, let's begin with method 1, the oxidation number method. I will guide you through the steps using problem 7.8 as our comprehensive example. We need to balance the reaction where potassium dichromate reacts with sodium sulfite in an acidic solution to yield chromium ions and sulfate ions. Step 1. Write the correct skeletal ionic equation for the reaction. At this stage, we focus only on the species that are involved in the redox change, typically ignoring spectator ions like K+ and Na+ stuff. They just watch.
So just the ions changing.
Yes. So our skeletal ionic equation is Cr2O72AQ plus SO32AR3 plus SO42XAQ. Step 2. Assign oxidation numbers to all elements in the skeletal equation and identify those that undergo a change. We did this before for some, but let's recap.
Okay. CR NCR2O7 to what?
In Cr2O72, oxygen is -2, 7 OEs plus 12. Each Cr is plus 6.
S in SO32.
In SO32, oxygen is -2, 3 O equals 9 equals 6. Overall charge -2, so S equals plus 4.
Cr3 plus C.
For Cr3 plus easy, it's plus 3.
S in SO42.
In SO42, oxygen is 9x2, 4O equals 8. Overall charge -2, so S plus 6.
Okay, so Cr goes from plus 6 to plus 3. S goes from plus 4 to plus 6.
Correct. Chromium Cr oxidation number decreases by 3. Sulfur S oxidation number increases by 2. This confirms dichromate is the oxidant, gets reduced, and sulfite is the reductant, get oxidized. Step 3. Calculate the total increase in oxidation number and the total decrease in oxidation number, and then make them equal by multiplying the appropriate species by suitable coefficients. This is the core balancing step.
Okay.
For chromium, the change is a decrease of 3 units per chromium atom. But notice there are 2 chromium atoms in Cr2O72, so the total decrease in oxidation number for one Cr2O72 unit is 2, 3 equals 6.
Total decrease is 6. Got it.
Sulfur. For sulfur, the change is from +4 to +6, which is an increase of 2 units per sulfur atom per SO32 ion.
Decrease is 6, increase is 2. Not balanced.
Right. To make the total increase equal to the total decrease, which is 6, we need the increase to also be 6. How do we get 6 from 2? Multiply by 3.
Multiply the sulfur species by 3.
Exactly. We need to multiply the sulfur-containing species, SO32 and SO42, by 3. And we also need to ensure the number of Cr atoms is balanced on both sides. Since we start with 2 Cr and Cr2O72, we need 2 Cr on the right, so we place a coefficient of 2 before Cr3 plus it.
Okay, so put 3 before SO32 and SO42, and 2 before Cr3 plus.
Correct. The equation now becomes Cr2O72 plus 3SO32 Beishu, ace 2Cr3 plus 3SO42 Beisho Q. Now the electron transfer is balanced conceptually. Step 4, balance the charges. This is where the medium acidic or basic comes in. The problem specifies acidic solution, so we will use H+ ions to balance the net charge.
Okay, calculate charges on both sides.
Calculate the total charge on the left side. -2 for Cr2O72 plus 3-2 for SO32, and we're going to do 6 and equals 8.
Left side is -8.
Right side. Calculate the total charge on the right side. 2 plus 3 for Cr3 plus 3-2 for SO42 plus 6 equals 0.
Right side is 0. Left is negate. How to balance with H plus 0?
The left side currently has a charge of -8 and the right side has a charge of 0. To balance this in an acidic medium, we must add H+ ions, which are positive, to the more negative side to make its charge equal to the other side. We need to add 8 positive charges, 8H+, to the left side to bring its charge from -8 up to 0.
Add 8H+ to the left.
So add 8H+ to the left. Cr2072-AQ plus 3SO32AQ plus 8H plus AQ plus Cr3 plus AQ plus 3SO42-Q. Charges are now balanced as 0 on both sides.
Yeah.
Step 5. Balance the hydrogen and oxygen atoms. We always balance hydrogen atoms by adding water H2O molecules. After that, we perform a final verification of the oxygen atoms.
Okay, check hydrogens.
On the left side of our current equation, we now have 8 hydrogen atoms from the 8H plus at. On the right side, there are no hydrogen atoms. To balance hydrogen, we add H2O molecules to the side that needs H. Since each H2O molecule provides 2 hydrogen atoms, we need 4 H2O molecules on the right to provide 8 hydrogens.
Add 4H2O to the right.
The equation becomes Cr272 plus AQ plus 3SO32AQ plus 8H plus A2A3 plus AQ plus 3SO42 plus 4H2L.
Now, the final check, oxygen atoms.
Finally, let's meticulously verify the oxygen atoms on both sides. On the left side, 7 oxygens from Cr272 plus 9 oxygens from 3SO32 equals a total of 7 plus 9 with 16 oxygen atoms.
16 oxygens on the left-right side.
On the right side, 3, 4 equals 12 oxygens from 3SO42 plus 4 oxygens from 4H2O, a total of 12 plus 4 plus 4 is 16 oxygen atoms.
16 oxygens on right, too. It's balanced.
Since both hydrogen and oxygen atoms are now balanced and the charges were previously balanced, this equation now represents the fully balanced redox reaction using the oxidation number method. This comprehensive approach is what you need for your exams.
It's a very clear step-by-step process. Now, let's try another example using the oxidation number method, but this time for a basic medium, problem 7.9. Permanganate ion, MnO4, reacts with bromide ion, Br, in basic medium to give manganese dioxide, MnO2, and bromate ion, BrO3.
All right, let's apply the oxidation number method to a basic medium reaction. This requires a slight adjustment in the charge balancing step. Step 4.
Okay, let's go. Step 1, skeletal equation.
Step 1. Write the skeletal ionic equation, MnO4AQ plus BrAQ plus BrO3.
Step 2, oxidation numbers and changes.
Step 2. Assign oxidation numbers and identify changes.
M is plus 7.
Br is minable 1.
M is plus 4.
Br is plus 5.
So Mn goes plus 7 to plus 4, decrease 3.
Right.
Br goes minus 1 to plus 5, increase 6.
Correct. Manganese Mn oxidation number decreases by 3. Bromine Br oxidation number increases by 6. This tells us MnO4 is the oxidant and Br is the reductant.
Step 3, equalize increase and decrease.
Step 3. Equalize the total increase and decrease in oxidation number. The total decrease for M is 3. The total increase for Br is 6. To make them equal, the least common multiple is 6. We need the total decrease to also be 6. How do we get 6 from 3? Multiply by 2.
Multiply the Mn species by 2.
Yes. We need to multiply the Mn-containing species, MnO4 and MnO2, by 2. The Br species already has the correct change of 6, so its coefficient remains 1 for now. So the equation becomes 2MnO4 AQ plus BrAQ, 2MnO2 plus BrO3AQ. Step 4, balance the charges. Now, the reaction occurs in a basic medium, so we use OH ions.
Okay, calculate charges again.
Calculate the total charge on the left side, 2-1 for MnO4 plus -1 for Br, reaching -1 and -3.
Left side is -3, right side.
Calculate the total charge on the right side. Charge on MnO2 is 0 plus -1 for BrO3.
Right side is -1, left is -3. How to balance with OH?
The left side has a charge of -3 and the right side has a charge of -1. To balance in a basic medium, we add OH ions, which are negative, to the more positive or less negative side to make its charge equal to the other side. The difference is 2 units -1 versus 3. The right side -1 is more positive, so we need to add 2 negative charges to a right side to bring its charge down from -1 to -3.
Add 2 OH to the right side.
Yeah. Oh. So 2MnO4AQ plus BrAQ plus BOO3AQ plus 2OHAQ. Charges are now balanced, -3 on both sides. Step 5, balance the hydrogen and oxygen atoms. Add H2O to balance H.
Check hydrogens.
On the right side, we now have 2 hydrogen atoms from the 2OH. On the left side, there are no hydrogen atoms. To balance hydrogen, we add H2O molecules to the left side. Since we need 2 hydrogens, we add 1 H2O molecule.
Add 1 H2O to the left.
The equation becomes 2MnO4 plus H2OL plus H2OS plus BOO3 plus 2OH. Final check. Oxygen atoms.
Finally, let's verify the oxygen atoms on both sides. On the left side, 4 oxygens from 2MnO4 plus 1 oxygen from H2O equals 9 oxygen atoms.
9 oxygens on right side.
On the right side, 2, 4 oxygens from 2MnO2 plus 3 oxygens from BOO3 plus 2 oxygens from 2OH, a total of 4 plus 3 plus 2 equals 9 oxygen atoms.
9 oxygens on right, too. Balance.
All atoms and charges are balanced. This is your final balanced equation in basic medium using the oxidation number method. That's a clear demonstration of the oxidation number method in both acidic and basic conditions. Now let's move to the second major approach, the half reaction method, also known as the ion-electron method. This one is often preferred for very complex reactions, I hear.
That's often true, yes. This method, the half reaction or ion-electron method, is incredibly powerful and systematic, maybe more methodical. It breaks down the overall redox reaction into two separate half reactions, one for oxidation and one for reduction, balances them individually for atoms and charge, and then combines them.
Okay, let's use problem 7.10. Permanganate ion, MnOr, in basic solution oxidizes iodide ion I to produce molecular iodine I2 and manganese I-tuxide, MnO2. Balance this ionic equation using the half reaction method.
All right, let's tackle MnO4 plus I, MnO2 plus I2 in basic solution using the half reaction method. Step 1. Write the skeletal ionic equation, same as before. MnO4 plus IAQ, MnO2 plus I2. Step 2. Separate the equation into two half reactions, one for oxidation and one for reduction. We need to identify the changes again. Mn goes from +7 in MnO4 to +4 in MnO2 reduction. Iodide goes from -1 in I to 0 in I2 oxidation.
Okay, separate them out.
So our oxidation half reaction is IAQ, IA2, and our reduction half reaction is MnO4, MnO2. Step 3. Balance all atoms other than oxygen and hydrogen in each half reaction individually.
Check I and M.
For the oxidation half, AI2, we have one iodine on the left and two on the right, so we need two iodide ions, two IQQs. Now, iodine atoms are balanced.
Okay, reduction half.
For the reduction half, MnO4-MnO2. Manganese atoms are already balanced, 1 Mn on each side, so nothing needed here for N step 4. Balance oxygen atoms using H2O molecules, and then balance hydrogen atoms using H+ ions, initially, even for basic medium. Then convert to basic. This is the key part, especially the conversion.
Okay, balance O and H in the reduction half first.
Let's work on the reduction half reaction. MnO4, AQ, MnO2. We have 4 oxygen atoms on the left and 2 on the right. We need 2 more oxygens on the right. Add 2 H2O molecules to the right side. MnO4, AQ, MnO2S plus 2 H2O.
Now hydrogens, 4H on the right.
Right. Now we have 4 hydrogen atoms on the right side from the 2 H2O. To balance hydrogen, we add 4H plus ions to the left side as if it were acidic for now. MnO4AQ plus 4H plus MnO2S plus 2 H2OL.
Okay, balance for acid, but it's basic solution. Now what?
Now, critically, the problem states this reaction takes place in a basic solution. So here's the conversion step. For every H+ ion we have added, we must add an equal number of OH ions to both sides of the equation. We added 4H plus RH, so we add 4 OH to both sides.
Add 4 OH to left and right.
Okay. MnO4AQ plus 4H plus AQ plus 4OHQ MnO2 plus 2H2O plus 4OHAQ.
Now what?
Now, combine the H+ and OH ions that are on the same side to form H2O molecules. On the left, we have 4H plus and 4H. They combine to form 4H2L.
4H plus 4OH becomes 4H2L.
Right. So the left side becomes MnO4-4H2O. Well, the right side is still MnO2S plus 2H2O plus 4OHU.
Okay.
Finally, simplify the H2O molecules. We have 4H2O on the left and 2H2O on the right. We can cancel 2H2O from both sides, leaving 2H2O on the left.
Cancel water.
MnO4 plus 2H2OL plus 4OH2. Now this reduction half reaction is fully balanced with respect to atoms, MnOH, in a basic medium. Step 5. Balance the charges by adding electrons E to the appropriate side, then make the number of electrons equal in both half reactions by multiplying.
Back to the oxidation half.
2IA2.
Charges.
For the oxidation half reaction, 2IAQ, IA2. The total charge on the left is 2 - 1 - 2. The total charge on the right is 0, 2 is neutral. To balance the charge, we add 2 electrons to the right side, more positive side. Loss of electrons equals oxidation. 2IQ plus 2E, oxidation half balanced for charge.
Okay. Reduction half. MnO4 plus 2H2O, MnO2 plus 4OH charges.
For the reduction half reaction, MnO4 plus 2H2O plus 4OH plus 4OHU. The total charge on the left is -1 from MnO4, water is neutral. The total charge on the right is 4 - 4 from 4OH, MnO2 is neutral.
Left is -1, right is -4. Need to add electrons to the left.
Correct. To balance the charge, we add 3 electrons to the left side, more positive side. Gain of electrons reduction, MnO4 plus 2H2OL plus 3E MnO2 plus 4OHE, reduction half balance for charge.
Now equalize electrons. We have 2E in oxidation, 3E in reduction.
Now, we need to ensure the number of electrons lost equals the number gained. We have 2 electrons in oxidation and 3 in reduction. The least common multiple LCM of 2 and 3 is 6.
Need 6 electrons in both.
So we multiply the entire oxidation half reaction by 3 to get 6E. 2 IQs plus 2E becomes 6 IQ, 3 I2s plus 6.
Okay.
And we multiply the entire reduction half reaction by 2 to get 6E. 2 MnO4 plus 2H2OL plus 3 MnO2 plus 4OH plus 4H2 plus 4H2O plus 6E MnO2 plus 8OHU. Step 6. Add the 2 balanced half reactions together and cancel out any common species, especially the electrons. 6 IQ, 3 I2s plus 6E plus 2 MnO4 plus 4H2O plus 6E MnO2s plus 8OHU.
Cancel the 6 electrons.
Yes, the 6 electrons on both sides perfectly cancel out, adding every everything else gives 6IAQ plus 4H2OL plus 4H2OL, 3CI2s plus 2MnO2s plus 8OHQ. Step 7, perform a final verification. Always double check atoms and charges.
Let's check. Atoms first.
Atoms check.
Iodine 6, manganese 2, oxygen 24 plus 4 plus 12, hydrogen 42, 8.
Iodine 32, 6 mix 1 for I plus 2 to NO4 plus 8, hydrogen 8.
Atoms match. Charges.
Charge check.
6 then 1 for I plus 2 to 1 for MnO4 and MnO6, 2 to S2NO8.
Charge on I2 0 plus charge on MnO2 0 plus 8 then 1 for OH equals -8.
Charges match too. Metaget 8 on both sides. Balanced.
The charges are also perfectly balanced. This confirms our equation is fully balanced using the half reaction method. This systematic approach, especially handling the basic medium conversion, will ensure you get full marks on such problems.
Applications of redox from titrations to electrochemistry.
That was an incredibly thorough walkthrough of balancing redox reactions, truly an indispensable skill for anyone preparing for competitive exams. Beyond just solving equations on paper, where do these powerful redox principles find their practical application in the real world? Our material specifically mentions titrations.
That's an excellent question, and it's where the theoretical understanding truly connects to practical chemistry, especially analytical chemistry.
Right.
Redox reactions have significant and widespread practical applications, and one of the most common and vital is redox titrations.
Like acid-base titrations, but for redox.
Fundamentally similar, yes. But instead of using a pH-sensitive indicator to find the strength of an acid or a base, we use a redox-sensitive indicator to accurately determine the unknown strength or concentration of an oxidant or a reductant solution.
Okay. Uses.
Oh, they are widely used in quality control for pharmaceuticals, environmental monitoring like checking water quality, food analysis, and various industrial analyses. Very practical.
How do the indicators work? Are they like litmus?
Not exactly like litmus, but they signal the endpoint using color changes related to the redox process. There are a few different clever types of redox indicators depending on the specific reaction.
Okay, type 1.
Firstly, in some cases, the reagent itself is intensely colored and acts as a self-indicator. The prime example here is a permanganate ion, MnO4.
Permanganate is deep purple.
Exactly. It possesses that vibrant purple color. During a titration, as it acts as a powerful oxidizing agent, it gets reduced, often to the colorless Mn2 plus ion in an acidic medium.
Purple to colorless.
So, as the purple permanganate solution is added dropwise from the burette to the reductant in the flask, its color disappears instantly as it reacts. Once all the reductant has been consumed, meaning you've reached the equivalence point, the very next drop of excess permanganate,
The first tiny bit that doesn't react?
even at a remarkably low concentration, will impart a lasting tinge of pink color to the solution in the flask. This precisely signals the endpoint of the titration with minimal overshoot of the reagent, making it incredibly precise.
Clever. The reactant itself signals the end. What if the reactants aren't colored?
Good point. Secondly, if the reagents themselves don't provide a dramatic color change, we employ an external indicator. These indicators are carefully selected substances that are designed to be oxidized immediately after the last trace of the main reactant is consumed, producing a sudden and dramatic color change.
So the indicator reacts right at the end?
Yes, just after the equivalence point. A good example involves the dichromate ion, Cr2O72. It is orange, and its reduced form, Cr3 plus Cli, is green.
Orange to green, that's a color change.
It is, but often it's gradual and not sharp enough for a precise endpoint determination. So we use an external indicator like the phenylamine. Just after the equivalence point, when all the reductant is gone, the excess dichromate oxidizes the diphenylamine indicator, which then undergoes a profound color change to an intense blue, sharply signaling the endpoint of the titration.
Okay, external indicators. Third type. You mentioned starch.
Thirdly, there's a widely used and particularly interesting method that relies on starch as an indicator, specifically for iodine. This method is commonly used when the redox reaction either produces or consumes iodine, I2.
Iodine and starch is the blue color, right?
Exactly, a very intense blue-black color. This method is often used in iodometry or iodimetry. For example, consider copper ions, oxidizing iodide ions, 2C2 plus IQ plus 4IQ plus I2AQ. In this reaction, elemental iodine, I2, is produced.
Okay, I2 is formed.
While iodine is generally sparingly soluble in water, it remains effectively in solution as a triiodide complex, I3, when excess potassium iodide, Ki, is present, allowing it to interact with starch.
Ah, okay, so how does the titration work?
In a titration using this method, after the iodine is liberated, like in the copper reaction, we add starch indicator, and the solution turns that deep blue. Then we titrate this liberated iodine with a standardized solution of sodium thiosulfate ions, S2O32.
Thiosulfate reacts with iodine.
Yes, they undergo a specific redox reaction, I2AQ plus S2O32AQ plus S4062AQ tetrathionein ion. As the thiosulfate is added from the burette, it reacts with and consumes the iodine.
And when all the iodine is gone?
When all the iodine has been consumed by the thiosulfate, the intense blue color suddenly and dramatically disappears. The solution becomes colorless, or the color of other ions present. This sharp disappearance signals a very clear and easily detectable endpoint.
Blue color vanishes. Sharp endpoint.
This allows for incredibly precise stoichiometric calculations of the original unknown concentration. For example, in determining the amount of copper in an ore sample or the amount of bleach in a commercial product.
The cleverness of these indicator methods is truly impressive. We've talked extensively about oxidation numbers and their utility. Are there any known limitations to this concept, or are there evolving concepts around them in higher chemistry? It seems so useful, but is it the whole story?
That's a very insightful and advanced question, and it speaks to the dynamic nature of chemistry. While the concept of oxidation number is incredibly practical and robust for bookkeeping, balancing equations, and solving competitive exam problems.
It works well for exams.
It does. But like any model, it does have its conceptual limitations. As we've seen, our understanding of redox processes has continuously evolved, from classical observations to electron transfer, and finally to this bookkeeping tool based on assumed charges. The oxidation number method, with its convenient assumption of complete electron transfer even in covalent bonds, is a powerful simplification.
A useful simplification.
Yes. However, in more advanced theoretical chemistry, especially when delving into molecular orbital theory and electron density distributions, a more nuanced perspective emerges.
What's that perspective?
Here, oxidation is more accurately visualized as a decrease in electron density around the atoms involved in the reaction, and conversely, reduction is seen as an increase in electron density around those atoms.
Thinking about electron clouds shifting rather than whole electrons moving.
Exactly. This approach is more sophisticated and aligns better with quantum mechanical understanding of how electrons are truly distributed in molecules, rather than assuming rigid whole number charges or complete transfers where they don't fully happen.
Okay.
While this advanced concept might not be directly tested in terms of calculation for your current competitive exams, it's vital to be aware that the field is constantly advancing, and simpler models like oxidation numbers are just that. Powerful models designed to simplify complex realities for practical application and problem solving. It's a concept that continues to evolve.
That's a great reminder that chemistry is a dynamic and ever-evolving field. Finally, let's connect redox reactions to electrode processes, a key link to electrochemistry. Can you explain how the fundamental concept of redox leads directly to producing electricity, the power behind so much of our modern world?
This is truly where redox chemistry transcends mere description and enables powerful technologies that underpin our daily lives. The connection between redox reactions and electrode processes is the cornerstone of electrochemistry.
Chemistry and electricity.
Exactly. It's the study of how chemical energy can be converted into electrical energy and vice versa.
Okay, how does redox do that?
Let's revisit our earlier competitive electron transfer example, the spontaneous reaction between zinc metal and copper, 2 ions. ZnS plus Cu2 plus Eq plus Qs.
Zinc gives electrons to copper ions.
Right. If you simply dip a zinc rod directly into a copper sulfate solution, the electrons are transferred immediately and directly from the zinc atoms to the copper ions right there at the surface.
Direct contact, direct transfer.
Zinc is oxidized, copper ions are reduced, and this direct transfer of electrons primarily results in the production of heat. This is what we call direct electron transfer. The energy is released, but mostly as heat, not useful electricity.
Okay, so direct contact equals heat. How do we get electricity?
To harness this chemical energy as useful electrical energy, we need to be ingenious. We must modify the experiment to force the transfer of electrons to occur indirectly, that is, through an external metallic circuit, like a wire.
Force the electrons down a wire.
Exactly. This necessitates physically separating the oxidation part from the reduction part into 2 distinct compartments. This is precisely what is achieved in what is known as an electrochemical cell, often called a galvanic cell or a voltaic cell after galvanium volta.
Okay, the cell setup. Let's visualize the Daniell cell from figure 7.3.
Let's visualize the setup for a classic example. The Daniell cell.
You use 2 separate glass beakers. In one beaker, you immerse a copper strip or rod into an aqueous solution of copper sulfate. CuSO4.
This is 1/2 cell.
Copper rod in copper sulfate solution. In the other beaker, you immerse a zinc rod or strip into an aqueous solution of zinc sulfate, ZnSO4. This forms the second half cell.
Zinc rod in zinc sulfate solution. 2 separate beakers.
The connections. The zinc and copper rods, which function as electrodes, are connected externally by a metallic wire. This wire typically includes a device like an ammeter or voltmeter to measure current or potential difference, and maybe a switch.
Wire connecting the 2 metal rods.
The salt bridge. Now, crucially, the 2 solutions in the separate beakers need to be connected somehow to complete the circuit internally. This is done using a salt bridge.
The U-shaped tube thing.
Yes, usually a U-shaped tube containing a concentrated solution of an inert electrolyte, such as potassium chloride, KCl, or ammonium nitrate, NH4NO3, often solidified with agar-agar jelly to prevent it from just pouring out but allowing ions to move.
Okay, what does the salt bridge do? Seems important.
It serves 2 absolutely vital purposes for continuous electrical flow. First, it provides electrical contact between the 2 solutions without allowing them to mix significantly. This prevents the direct reaction we saw earlier and ensures that the electron transfer is forced through the external wire.
Connects the solutions, keeps them separate.
Second, it maintains electrical neutrality in each half cell by allowing the migration of ions between them. Think about it. On the zinc side, Zn is becoming Zn2 plus M, making the solution positive. On the copper side, Cu2 plus is becoming Q, removing positive charge, making the solution negative.
Charge builds up.
Without the salt bridge, this charge buildup would quickly stop the electron flow. The salt bridge allows negative ions, anions like Cl or NO3, to move towards the zinc side to balance the Zn2 plus charge, and positive ions, NKations like K plus or NH4 plus, to move towards the copper side to balance the loss of Cu2 plus. It completes the internal circuit.
Allows ions to move, keeps things neutral. Okay, so what happens when you connect it all?
When the switch is closed and the circuit is complete, you will observe something remarkable. First, electrons now flow not directly from zinc to copper ions, but specifically through the external metallic wire connecting the 2 rods. The ammeter will register a current. Electrons flow from the zinc rod, where oxidation occurs, Zn2 plus 2e, to the copper rod, where reduction occurs, Cu2 plus 2e.
Electrons flow Zn to key through the wire.
Second, inside the cell, the circuit is completed by the migration of ions through the salt bridge, as we just discussed, maintaining neutrality.
Okay, why do the electrons flow?
The very fact that current flows implies that there is a potential difference of voltage between the copper and zinc rods, the electrodes. This potential difference is the driving force, the push, that propels the flow of electrons through the wire, thereby generating electricity from the chemical reaction.
A voltage between the electrodes.
The potential associated with each individual electrode, like the zinc rod in zinc sulfate or the copper rod in copper sulfate, is known as its electrode potential. These potentials fundamentally arise from the inherent tendency of the chemical species at that electrode to either gain or lose electrons.
Tendency to gain or lose electrons creates potential.
To allow for standardized, comparable measurements across different systems, we define the standard electrode potential, E-chord. This is the electrode potential measured under very specific standard conditions.
Standard conditions.
Yes. When the concentration of each chemical species participating in the electrode reaction is exactly unity, usually 1 molar, if any gas is involved, its partial pressure is 1 atmosphere or 1 bar, very close, and the temperature is precisely 298 Kelvin, 25 degrees.
1 M, 1 at AM, and 298 K.
Okay. Is there a 0 point?
Yes. By universal convention, the standard electrode potential of the standard hydrogen electrode, SHE, which involves H plus ions and H2 gas under standard conditions, is arbitrarily set as our reference point, 0.00 volts. Everything else is measured relative to this. SHE equals 0.000 V. Got it. So what do the E values mean, like for zinc and copper?
The value of the standard electrode potential, E for any given electrode process, provides a quantitative measure of the relative tendency of the active species to be reduced, gain electrons. These are usually tabulated as standard reduction potentials. You'll find these in tables like table 7.1 in your notes.
Okay, interpreting the values. Negative E GAC.
Here's how to interpret the EA values, standard reduction potentials. A negative E value, like for Zn2 plus Zn, which is a mode of 0.76 V, means that the redox couple is a stronger reducing agent, the reduced form Zn is stronger, than the H plus H2 couple. This indicates that elemental zinc has a greater tendency to lose electrons, get oxidized, compared to hydrogen gas. The negative reduction potential means the reverse reaction, oxidation, is favored relative to hydrogen.
Negative E equals stronger reductant, like Zine, good at losing electrons, positive E.
A positive E value, like for Cu2 plus Q, which is plus 0.34 V, means that the redox couple is a weaker reducing agent. Cu is weaker than the H plus H2 couple. Or, looking at it the other way, the oxidized form, Cu2 plus, is a stronger oxidizing agent than H plus Ki. This implies that Cu2 plus has a greater tendency to gain electrons and be reduced compared to H plus E.
Positive E agrees. Weaker reductant, stronger oxidant, like Cu2+, good at gaining electrons.
Exactly. Looking at table 7.1, you can clearly see a trend. Species with higher, more positive E-degree values are stronger oxidizing agents, greater tendency to be reduced. For instance, fluorine, F2F, is at the very top with E degrees plus 2.87 V, making F2 the strongest oxidizing agent. It desperately wants electrons.
Fluorine wants electrons most. Highest E degree, strongest oxidant.
Conversely, species with lower, more negative E degree values have oxidized forms that are weak oxidants, meaning their reduced forms are strong reducing agents, greater tendency to be oxidized. For example, lithium, Li plus Li, is at the very bottom, with E degrees implying elemental lithium is the strongest reducing agent known. It very easily gives up its electron.
Lithium gives electrons most easily. Lowest E, strongest reductant.
This electrochemical series, precisely derived from these standard electrode potentials, is an incredibly powerful predictive tool in chemistry. It allows us to predict the spontaneity of countless redox reactions just by comparing E values, and forms the bedrock of understanding how batteries, fuel cells, corrosion processes, and even electroplating work.
So much relies on this series.
You will learn much more extensively about electrode reactions, electrochemical cells, and the NEET equation, which deals with non-standard conditions, in your detailed Class 12 electrochemistry curriculum. This is fundamental for modern technology. Outro.
And that brings us to the end of our comprehensive deep dive into redox reactions.
Oh, wow.
From the fascinating classical definitions and the electron transfer perspective, to the precision of oxidation numbers, the intricacies of balancing complex equations, and their profound connection to generating electricity, we've truly covered a vast and vital landscape of chemistry.
Indeed. We've established that redox reactions are a fundamental class where oxidation and reduction occur simultaneously. We've seen they're defined rigorously by both electron transfer and changes in oxidation numbers.
Right.
We meticulously explored their classifications: combination, decomposition, displacement, and that unique disproportionation reaction type. And most importantly, we mastered the systematic balancing techniques that are absolutely crucial for your exams.
Those methods are key takeaways.
Yes, before finally touching upon their critical applications in analytical titrations and the fundamental principles that govern electrode processes in real-world devices like batteries.
And the concept of the electrochemical series stemming directly from competitive electron transfer is particularly mind-bending, isn't it? Offering a glimpse into how simple chemical reactions can be harnessed to become a powerful source of electrical energy.
It really is profound.
It truly underpins so much of modern technology, from the compact batteries in our smartphones to vast industrial processes that shape our world.
Precisely. So, to truly solidify your understanding of this chapter and to confidently excel in your upcoming examinations, remember these key strategic points. First, revisit and ensure you thoroughly understand the definitions of oxidation, reduction, oxidants, and reductants from all three perspectives. We discussed classical, electron transfer, and oxidation number.
Know all the definitions.
Yes. Make sure you can fluently switch between them and apply them correctly in any given scenario you might face in a problem.
And second, this is non-negotiable, I think you'd agree.
Absolutely.
Practice, practice, practice. The balancing methods, especially the ion-electron method and the oxidation number method.
You have to practice. These systematic approaches are guaranteed to appear in your competitive exams, and proficiency here will directly translate to higher scores and greater confidence. Don't just watch, do the problems yourself.
Good advice.
Finally, to consolidate your learning, I strongly advise you to go through past year questions based on this lesson immediately, while it's fresh in your mind.
Apply the knowledge right away.
Yes. As you practice, try to visualize the processes, think about the electron movement or the ELN changes, and connect them back to the real-world phenomena we discussed. If any doubts arise as you practice, and they probably will, remember, the ultimate goal is absolute clarity.
Don't leave doubts hanging.
Never. Feel free to reach out with your questions, review the material again, discuss with peers or teachers. Consistent revision and persistent doubt clearing are your strongest tools for success in these competitive exams.
That's excellent, actionable advice for all our dedicated learners. Thank you for joining us on this essential deep dive. Stay curious, keep learning, and we'll be back soon with another vital topic to help you ace your exams.